All right, so last time we started internal loads, I assigned just one problem. So we have to just get to enough material that you can work on some more problems. Um, Anybody have any questions about that one problem I assigned? Um,
I have to ask again. So you have to do the full problem like we've been doing it to get that pin or that roller force, and then
yes, that's right. So first you have to calculate the external loads. Um, and then And then after you have the external loads, then you can start doing your cuts. And the key, let's say, let me call them the cutoff points. For the cuts are places where there are point forces, places where there are point couples, and places where the distributed load function changes. We haven't done distributed loads yet, but we're doing that today. And so, for example, if you have, so let's say after you calculate your external loads, you have some force there, you have a distributed load function here, you have a point force here, and another force. Let me think that's not possible. And say you have another force there. Okay. So, your cutoff points are going to be where this distributed load function changes, where this point force is. And so the cuts that you're going to do are going to be so first you're going to do a cut here where you're not including the entire distributed load. Your second cut is going to be, you're just looking at those cutoff points. Whoops. So this time you're going to go past the end of the distributed load, but damn it. So your second one is going to go past the end of this whole distributed load, but not get to that point force. And then your third cut is going to go past that point force, but not all the way to the end. And so these are the free bodies you're going to be working with. Yep.
So it's almost always easier to break up a problem into chunks and then solve part of it before moving on to another part. Is it ever easier to just leave all of the unknown forces on the total body as variables and then just do it all as one big row echelon form?
No, it's never easier. In deform, we will have to do that sometimes, but when you have to do it, it's a bummer. Yeah.
So, I'm sorry, I kind of missed that first part. So cut one, is that at that 2/3 of the triangle?
No. So remember that what you're doing with these cuts is you're just coming up with a single sort of a general free body that represents a whole range of a whole interval of x values.
Okay.
And so all we're doing there is we're saying, and so remember that what we're going to do is we're going to say this distance is x, and we're going to do everything in terms of x. Okay. Then we're going to say for the next one that this is x. And we're going to do everything in terms of x. And then last, we're going to say this is x. So we're not choosing a point where we're going to cut it. We're just choosing places that are, so notice that, so here's the idea. Okay, so this cut represents so this represents everything from here
You know,
with the,
is that the tiny distributed line
yes,
on top?
right, to just before you get to the end of the distributed load.
Right, because either way, it's kind of a function of like
Yeah.
that slope.
Yeah, either way, qualitatively it's the same. You have the same loads acting on it.
As functions.
Yeah, right. And then this one goes all the way from a billimeter after the distributed load to just the tiniest little amount before you get to that point force. Okay, that's the range of x values that we'll include there. And then this one goes from just after the point force to just before the end point. Okay, so each of those, but you can see we have to do these differently because this free body diagram in cut one looks qualitatively different than the one in two. In one, we don't have any space between the end of the distributed load and the end of the free body. Okay. In cut two, we do. In cut three, we have this point force that we don't have in cut two. And so that's why these are the cutoffs where your general earlier free body diagram can't represent it anymore. Okay. Okay, so let's talk about doing this in the presence of distributed loads. So internal loads in the presence of distributed loads. So let's say that we have a body like this, and we just have forces here supporting it, and then we have this general distributed load function. And this function is we're going to call this Q of x, That's what we're always going to call this distributed load function. And we're always going to assume that this is down. So down is a positive value of Q. And I mentioned this when we first talked about distributed loads, but it really didn't have much relevance yet. But now, I'm going to say it again. So remember this. You can't replace a distributed load with an equipolant point force until you've chosen the body to isolate. Okay, so what we're not going to do is right away figure out the centroid and the area of this distributed load and treat this whole internal loads problem as if there's just a single point force. Okay, we're not going to do that. What we're going to do instead is for each cut, we're going to replace the distributed load on that cut with an equipolant point force. And so remember that the rules for that is the area of the distributed load shape is the point force magnitude. And the horizontal centroid location is the location of that point force. So we'll go like so in this example above, we'll do a cut. It won't cover the whole beam, and it'll go like this. Okay. We're only including the part of that distributed load that's on the piece we're isolating. And then we have our internal loads like this. And so now that we've chosen the piece to isolate, now we can look at what we have here and find the centroid and the area. And now we can calculate those internal loads. Okay, so this is the equipolant point force. Okay, so let me show, we'll just start out with some simple examples and go to more complicated stuff. So the first example we're going to do is notice that when you're calculating internal loads, you have to treat weight like a distributed load. Okay. So let's say that we have a horizontal beam and a roller here at the end. Let's say that the length is 2 meters. And the mass of this thing is 30 kilograms. And we want to calculate the internal loads. Eventually, you're going to skip a lot of these steps, but at the start, I'm just going to go through kind of as many steps as I can think of. So first, I'm going to draw a free body diagram. Well, let's first calculate the external loads, I guess. So to do that, we're going to isolate the whole body. And so we have a force vector here. I'll call that RA. And God, an upward force there. And then the weight, okay, the weight is a distributed load, but now we've chosen the body to isolate. I'm going to put it down as a distributed load. So the total weight is 30 times 9.81. And so the total weight is 294.3, 294.3. But we're splitting it up over this 2 meter thing. And so I'm going to write this as a uniform distributed load that has a height of 294.3 newtons split over 2 meters. And so that's equal to 147.15 newtons per meter. Okay. Well, I mean, we've done external load calculations all the time, so we're used to just jumping right from the distributed load to the point force. And so now that we've chosen the body to isolate, I'm going to replace this distributed load with the equipolant point force. And as we know, the centroid of this rectangle is right in the middle. The magnitude of that point force is the area of that, which is 294.3. Okay, but notice that I didn't jump from the distributed load to the point force until I was clear to myself about what the body was that I'm isolating. Okay, so now we can do this calculation, and all we're going to get is that Newton's second law and rotational Newton's second law is going to say that RA is 147.15 and RB is 147.15. So now we can go to the cuts, the internal loads. Is everyone with me on this? So So now that we have the external loads, we're going to go to the cuts and the internal loads. Okay, well, I'm going to start out by redrawing the free body diagram of the whole thing. We know now that we have a force of 147.15 up, another one over here of 147.15. And then we have this distributed load with a magnitude of 147.15 newtons per meter. I guess I'll put the units in just so we don't get confused about what's a force and what's a distributed load. Okay, so now we have to identify all the cutoff points. Okay, well, we have the two ends. And now in the middle, are there any point forces, point couples, or places where our distributed load function changes? No. No point forces, no point couples, and no changes in the distributed load function between the endpoints. So how many cuts are we going to need? We can do this with just a single cut. Okay. So just one cut. And okay, so let's do the cut. So our cut one, since we only have one of them, this is valid for any x's between 0 and 2. Okay, this represents the whole beam. And like I said, it doesn't ever represent the endpoints, but we're not too worried about that. That's really just an issue with representing point force, representing slightly distributed loads as perfect point forces. Okay, so here is our cut. And we're ignoring all of this. And we have this force of 147.15 here. And we have this distributed load of 147.15 newtons per meter here. And we're ignoring all of this and this upward force. Okay. And since we're not including this light blue part, we have the loads that the light blue part applies to our free body. So that's our free body diagram. Okay. And this length here, what's this distance? We're not necessarily, so remember that this is x, exactly. Stop talking, we know. Okay, so it always goes from, your cuts always go from all the way at the left end point, your left is over here, all the way to some x value, and that x value has to fall within this range. Okay, so this is sort of like a general thing. Okay, so now we want to represent this now that we've chosen the body to isolate, we want to represent that distributed load as a point force. Okay, so let's think about the shape. This is a pretty simple shape. The height is 147.15. The width is x. And so the magnitude of this point force, we're just calculating the area of this rectangle, is 147.15x. And the centroid of this shape, we only care about the x location of it because it's a downward force, so we can move it along its line of action up or down anywhere. This is x over 2. Okay. So now I'm going to redraw this with the point force replacing the distributed load. We have an upward force of 147.15. We have the downward force that's replacing the distributed load now. It's at the midpoint and it has a magnitude of 147.15x. And then we have the internal loads, T, V, and M. Okay. Any questions about this whole process? First, we calculated the external loads. We've done that a million times. These are very easy rigid body problems. And then we go to the cut. And the key thing is that you don't replace the distributed load with the point force until you choose the cut. So now we've done it, and now we can just go through and in general, we're going to have our internal loads as functions of x. So Newton's second law says 0, positive 147.15 plus, remember that I said the directions, you know, it can get confusing what you're calling positive and what you're calling negative. Just remember that the labels that we put on here are what you're multiplying by a unit vector. And the unit vector is given by the direction of the arrow. Okay, so this 147.15x, the arrow says it's in the negative y direction. So that unit vector is 0, negative 1. And we're multiplying it by this function. So this is 0, negative 147.15x. And then T0 plus, this again is in the negative y direction, so this is 0, negative v is equal to zeros. And now you're just solving for those distributed loads. T is equal to 0. V is equal to negative 147.15x plus 147.15. With me on that? And then we'll go to the moment equation, and always on these internal loads, it's not that you have to, but it makes the math a little simpler, and really you just want to do it the same way every time so you don't make dumb mistakes. Our about point is going to be over here on the left, always on the cuts. Okay, so now we're going to do the moment equation. That upward force of 147 doesn't produce a moment. Does that 147.15x make it rotate clockwise or counterclockwise around that point? Clockwise. Yeah. So clockwise means it's negative. So we have negative. What's the moment arm?
X.
Nope. Yeah.
Oh, yeah, yeah.
Because that, yeah, right. So this distance here is x over 2. That's what we got from the centroid. And so we have negative x over 2 times 147.15x. Then add on the couple. And then it's always going to appear this way, but let's just think about it this time. What's the moment arm of this V? That one is going to be X. And is that clockwise or counterclockwise? Clockwise. So minus Vx is equal to 0. And now we're just solving for m. So m is equal to, so divide this by 2. I don't think I can do that in my head. Okay, so we have 73.575x squared plus Vx. But we've already calculated V. So now we can say m is equal to 73.575x squared minus 147.15x times another x plus 147.15 times x. Is everyone following where I'm getting that stuff? Okay, and now usually on these, you can add up some terms. We have 2 of these x squared terms. So our final answer for m is negative 73.575 x squared plus 147.15 x. Okay. One thing to start noticing, here's a crazy coincidence. Dm dx of this function is equal to v. There's no way that's going to keep happening.
I get the feeling that's going to keep happening.
Okay, so if you want to visualize what's going on with these, obviously T, we don't have to visualize that. There's no internal tension or compression. But let's graph out V versus X. And there are no cutoff points, so I'm just going to graph this function over the whole thing. Let's see. So it starts at 147.15. It ends at negative 147.15. It's a linear function. I missed. Damn it. Harder than it looks. This should not be the most complicated part of these, though. Okay, so it's a linear function that goes from positive 147 to negative 147. And then, and if you ever need to do these, I mean, this isn't a class on graphing functions, so, you know, on homework or whatever, just do it in, what's that,
Desmos?
program you guys all like? Yeah, Desmos. All the kids like it. Kids today.
They're crazy graphing software.
We used to have to draw graphs in the sand with a stick.
Uphill both ways.
Okay. So what do we got here? We got it's going to be 0 at this endpoint. It's going to be 0 at this endpoint too. And then it's going to be, what's it going to be at its highest point? You know, it's just going to be a parabolic function like this. And at 1, it's going to be 73.575. Okay. So, what can you say about where you're worried about this thing breaking? Not too much in this case, because what we have is the magnitude of the shear force being biggest at the endpoints, and we have the magnitude of the bending moment being biggest at the center. So it just depends on, you know, whether your material and your geometry is more susceptible to bending or shear force and stuff like that. So there's nothing really we can say about this. Eventually, when you take deform and you learn to calculate stresses and strains, then we'll be able to evaluate, you know, where the stresses are bigger, you know, strains are bigger. One other crazy coincidence. Notice that, so this is a constant function, right? And so this 147.15 here is actually our function Q of X. That's our distributed load function. Okay, that's not going to be, it's not going to be quite as simple as that when we get to more complicated functions. But in this case, that's just the function. It's just a constant, right? Well, notice that negative dv dx is equal to, and I did it as a function before, so negative dv dx as a function of x is equal to q of x. Okay. And so this is going to keep happening, but for now, you don't, you know, we'll talk about it, get it in your notes and stuff later, but okay.
So maybe I'm getting ahead of you. I'm
Yeah.
sure I am.
Yeah.
But does that mean that you can just like kind of just take the derivative and
Yeah. Well, so if you look at, it would be nice if you could take the derivative because then you don't have constants of integration, you know? Well, the thing that's a pain to calculate is the moment, okay? And in order to calculate the moment through Newton's laws, you need to already have calculated the shear force. So the direction that you can do what you're talking about is actually an integral. And then you have to deal with all the boundary conditions and stuff. It's kind of a pain. So yes, you can do it. There are some cases where it's easier, but we're just going to go through Newton's laws and use these derivative relationships as a check. Okay. But I'll point out, when we get into a couple of like really complicated examples, I'll point out cases where like, yeah, actually in this case, and not very often, but in this case, using that integral makes it a little faster probably, but not that much faster, because finding those boundary conditions is a super pain too.
Because you're like solving for C basically.
Right. Yes. And you have to do it at all of the places where the distributed load functions change and stuff, you know. So, okay, let's do let's do another example. So this time let's do one where we have so let's say we have a cantilever beam and a triangular distributed load. Computer. And let's say that the height of this is, so at its maximum, it's 1,000 newtons per meter. And let's say that the distance is 3 meters. And let's say for this one, we're going to ignore the weight. And we want to calculate the internal loads. Okay, we usually start by calculating the external loads, but notice that in this case, since our cuts never get to the right endpoint, our last cut never gets to the right endpoint, the external loads won't come into this problem. And so I'm just going to leave them off. I mean, just in the interest of time. So these external loads won't appear in the cuts.
And by that you mean like the forces from the wall?
Right, and the couple, because that's a fixed joint. So I'll just skip this for time.
But doesn't, since the distributed load changes though, don't you need to cut for that?
Well, it's not a question of whether the distributed load changes. It's a question of whether you're representing it with a new function. And we're going to represent this with the same function the whole way. And that function is going to be the equation for a line. Okay? And so, so our free body diagram of the whole thing looks like this. We have these things that we don't know what those are. And then we have this distributed load. And I am going to express this distributed load as the function Q by finding the equation for this line. Okay, so how do you find the equation for that line? Well, the slope is the rise over the run. So the rise is 1,000 and the run is 3. And plus x. And then when x is equal to 0, the distributed load is at 0.
Plus x?
This is x equals 0.
Oh.
This is x.
Yep. You said
And-
plus x and then I saw times x.
Okay.
Gotcha.
So this function is 333.3 repeating x. Okay. So now looking at this, how many cuts do we have to make? Just one cut. So there's no cutoff points. So just one cut. And so cut 1 is valid for x's between 0 and 3. And so we're including some, not including some. We're including this. We're not including this. The length, well, we have the internal loads. The length of this piece is X. And so what's the height of the triangle at the right end of this cut? It's not 1,000 because we're not getting all the way there.
The slope for that, right?
Yep, so it's just that Q function because our X is at the end. Okay, so this is just going to be a height of 333.3 X. Now that we've chosen the piece to isolate, now we can go to a point force representation of this. And we're going to do that just by using the formula for a right triangle, where our height is 333.3 repeating X, and our base is X. Are you with me on that? So the area is base times height over 2. So that is 166.6 repeating X squared. And the centroid is if this whole base is X, then this is 2X over 3. That's just from the centroid formula for a right triangle. And so now we can redraw the free body diagram. And we have a downward force of 166.6 repeating X squared. And then we have the internal loads, and that's it. Any questions about that? And we know that this distance is 2X over 3. So now Newton's second law says 0, negative 166.6 repeating X squared plus T0 plus 0 negative V is equal to zeros. I keep not putting forces in that give you internal tension, but we got 0 for tension again. That's not always the case. And V is equal to negative 166.6 repeating times X squared. And then go to the moment equation. Would that 166 X squared force make it rotate clockwise or counterclockwise? Good job, Nicole.
Yay, I learned.
Negative, so we got negative moment arm of 2X over 3 times 166.6 repeating X squared. And then plus M minus Vx is equal to 0. And so M is equal to, this comes out to be 111.1 repeating x cubed plus Vx and then we already know V, so plug that in. So M is equal to 111.1 repeating x cubed minus 166.6 repeating x squared times another x. So this is also x cubed. And so we get M is equal to negative 55.5 repeating x cubed. And notice that dm dx is equal to V. Okay. And notice that negative dv dx if you take negative dv dx, you get positive 333.3 repeating x, and that's equal to our function q.
So maybe can you do that, like if you know that your distributed load starts at 0 at the left.
Yeah, that's a good point.
Then
Yes.
you can integrate.
Yes, that's right. That's right. Okay, any questions about that? All right, I'll give you a couple of problems to do with distributed loads, and then let's just spend Friday, like, bring questions that you have if you have trouble with any of them, or we'll just do examples or whatever, and we'll just spend a lot of time now doing problems. Okay.